In this video, we're going to review the covalent bonding part of Chapter 6. Covalent bonds are always formed between two nonmetals or a nonmetal and a metalloid. They involve sharing of electrons that have similar electronegativities, and because of that, the sharing must occur. It cannot be a swap of electrons in the way that ionic bonding happens. Bond length is the average distance between nuclei. When you go from a single to a double to a triple bond, the bond gets shorter. Additionally, as you go from single to double to triple bond, the bond gets stronger. The bond strength is just the energy required to break the bond. Lewis structures are used to depict covalent molecules. The lines that you see here, they represent shared electron pairs. In a Lewis structure, the total number of bonding and non-bonding electrons is the sum of the valence electrons in the atoms involved. In this case, we have 6 for the oxygen and 2 for the hydrogen total, so that's 8 total, and we have 2, 4, 6, 8 electrons shown in this structure. When you're drawing a Lewis structure, make sure that you satisfy the octets for all atoms by using lone pairs as necessary and/or double or triple bonds as necessary. Resonance can exist when you see an alternating single-double bond pattern. If we look at O3 right here, I just as easily could have drawn the double bond on the other side. And the truth of the matter is that neither of these two structures is the actual structure of O3. The true structure is the average of these two resonance structures. On to geometry. Vesper theory stands for valence shell electron pair repulsion. Simply put, electrons repel one another, and that causes bonds and lone pairs to be as far apart from one another as possible. In general, you'll get an even distribution around a central atom of all the different electron domains. And that's why the structure on the left didn't make any sense. The structure on the right has an even distribution of electrons around the oxygen. Steric number is a term often used in molecular geometry. It is simply the number of atoms and lone pairs around a given atom. So if we look at the boron here, its steric number is 3 because there are 3 atoms to which it is bonded and no lone pairs. In the case of the carbon here, there are no lone pairs on the carbon, and there are still 3 atoms around that carbon, even though there's a double bond. On to electron pair geometry. There are only 3 options for it. There's a linear, trigonal planar, and tetrahedral, when the steric number is 2, 3, or 4 respectively, and the bond angles are as shown. With molecular geometry, we get a little bit more deviation. Lone pairs result in there being different names. So for example, when the steric number is 3, if there are 3 atoms to which the central atom is bonded, then that is going to be trigonal planar. However, if there is an electron pair and 2 atoms, then it will be bent. For a steric number of 4, we have tetrahedral if there are no lone pairs. With 1 lone pair, there's trigonal pyramidal, and with 2 lone pairs, there's bent. We've already seen the main bond angles. However, if there are lone pairs on the central atom and we're trying to figure out what the angle is, then the angle is always going to be less than, or in this case, where there are 2 lone pairs, less than what you would think. So for H2O, it's less than 109.5. On to polarity. Bond polarity results from an unequal sharing of electrons in a bond. You can tell if a bond will be polar based on the difference in electronegativities of the atoms involved in it. O is more electronegative than H, and therefore the electrons will tend more towards the oxygen, creating a partial positive on the hydrogen and a partial negative on the oxygen, and a dipole moment that points in the direction of the more electronegative element. If the electronegativity difference is 0.4 or less, there isn't enough polarity to really make the bond polar. So a carbon-hydrogen bond is essentially nonpolar. Next, we have molecular polarity, which also results from an unequal sharing of electrons. The important thing to understand here is that bond dipoles can cancel each other out if you have symmetry. Carbon to oxygen bonds are polar. However, in the case of CO2, because they are equal in magnitude and opposite in direction, the 2 dipole moments cancel each other out, and there is no net dipole moment. A net dipole moment happens when, if you combine the different dipole moments from the bonds, there is a resultant. For example, in H2O, the 2 bond dipoles result in this net dipole moment. As a tip, if there is a steric number of 2 to 4 and you have a lone pair, you will always have a net dipole moment because you will never have a symmetrical molecule. And we can see that in the examples of SO2 and NH3. That's all for this video. I hope it's been helpful. Feel free to leave any questions or comments in the comments section below, and thanks for watching.